So we did not use this thing together. Increasing sequences have limits always, whether it is bounded above or not. If it is bounded above, it has a finite limit. If it is not finite, of course, limit is infinity, plus infinity. Bounded below sequences always have a limit. If it is bounded below, it has a real number as a limit, finite limit. If it is not bounded below, limit will be minus infinity. So what is important is increasing monotone sequences always have limits. Monotone and bounded sequences have finite limits. Proof is not difficult, but the result is very, very, very important. So here, what does he say? Etc. These are not important. Proposition 6.3 asserts that the limit of a monotone sequence exists, but does not directly say what. Yeah, that is what is very important is that what important is it says there is a limit, existence only. We don't know what the limit is. For instance, Beethoven, we don't know the limit. Example is that if you take this sequence 1 plus 1 over n raised to the power n, this is increasing. This is increasing and this is bounded above. So it has a limit. Nobody knows to this day how to write the limit. So as a result, we say this limit is, we write limit n tends to infinity, 1 plus 1 over n raised to the power n is equal to E. Actually this, according to him, he writes something like that, 2 dots. This is E. You can show that 1 plus 1 over n raised to the power n increasing, actually strictly increasing. You can prove it. And you can prove that this is less than or equal to 3. So it's strictly increasing, bounded above by 3. Then it has a limit. Nobody knows what the limit is. So this is a transcendental number. Transcendental. I hope my spelling is correct. I think transcendental. Incorrect. Transcendental number. Transcendental means E is not a solution of a polynomial equation with integer coefficients. So as a result, we cannot write it. So this is one application of this result. Of course, there are many. Even 1 minus 1 over n raised to the power n. This one also for n grade going 2 to infinity, I guess it is, cannot remember exactly, that is also strictly increasing. And it has a limit. What is funny is, this limit is e to the minus 1. These are interesting things. This is a very, very important result. Because if you are studying alone, you may wonder what sequences converge. This is one, monotonically increasing, bounded above, monotonically decreasing, bounded below. And of course there are others. So, and of course Cauchy sequences converge, whether they are increasing or actually converges if and only if. I guess that theorem is coming soon. Here proposition 6.3.10, let 0 less than x less than 1, then we have limit x to the n is equal to 0. This can be proved, but let's go through the proof anyway. since 0 less than x less than 1, one can show that the sequence is decreasing. That is clear. X to the n plus 1 is strictly less than x to the n if x is less than 1. On the other hand, the sequence has a lower bound 0. For any n, x to the n is strictly greater than 0. So it is decreasing, strictly decreasing and bounded below. By this theorem, it has a limit. Then we don't know what the limit is. We want to prove the limit is 0. He says since x to the n plus 1 is equal to x times x to the n, we thus see from the limit lows that x to the n plus 1 converges to xl. If x to the n converges to L, x times x to the n plus 1, x times x to the n converges to xl. Right? But the sequence x to the n plus 1, n going 1 to infinity is just the sequence x to, maybe I should write otherwise confusing. X is between 0 and 1. So, as a result, x to the n plus 1 is strictly less than xn, greater than 0. Strictly decreasing bounded below, therefore, limit n tends to infinity, x to the n exists. Right? By that theorem, and that is, let's call it L. Then he says, he now considers x to the n plus 1. X to the n plus 1 is x to the n times x. So he says the limit of n tends to infinity, x to the n plus 1 is limit n tends to infinity, x to the n times x is limit n tends to infinity, x to the n times limit n tends to infinity, x. Limit of x to the n is equal to L. So I can write here this L. And this is a constant. Constant is, limit is the same thing. But x to the n plus 1 is the same sequence, no? Because you start from 2, x to the 2, x to the 3, like that. So this limit is actually L. L is equal to Lx. Therefore, if you take L to one side, then you get 1 minus x is equal to 0. And since x is strictly less than 1, this guy is not 0. Since 1 minus x is not 0, L must be 0. So that is his proof of limit. Actually, on the other hand, you can prove decreasing sequences converge to infimum of the sequence. So you can actually prove that infimum of, you can do this thing, x to the n, n belongs to n, n belongs to z plus is equal to 0. This you can prove. You can prove it. Indirectly, this is a proof of it. No? I'm saying without this kind of approach, this is kind of tricky. No? You can directly prove that the infimum is 0. Anyway, so we have proved it. Then you have some exercises. Note that this proof does not work when x greater than 1 these days. When x greater than 1, of course, this sequence is not bounded above. It is not. So it doesn't work. Again, these exercises verify the claim in exercise 6.3.4. What is it? That's not the problem. Prove proposition 6.3.6. What is it? I almost did it. Then prove proposition 6.3.8. 8, I asked you to prove, I need to discuss it. 6.3 point, and something here he says, I didn't read the problem, but it's not difficult. Now let's go to limit and limit. Points. Limit, and limit. Before you go, now maybe I can collect it now. That you are supposed to give me solutions to 2 problems. And written ones.
Yeah, the videos have been on the tab before I go, I'll write it on paper and
Okay. We are going to talk about some word called lim sup, lim min and limit points. So 3 words are new words for us. We haven't seen lim sup before, we haven't seen lim min before, and we have seen limits but not limit points. Let's see. Consider the sequence 1.1 minus 1.01, 1.001, minus 1.3071, plus 1.4071. If one plots this sequence, so I am unhappy about he never plots anything. So students don't get the physical feeling. To do maths, intuition and insight are very important. These are the 2 key things. You have to have intuition. By doing things, you get. Insight means, if you want to talk about, say, waterfalls in this country, say you want to prove, say, Babarakanka Falls is the tallest fall. No, I can, as I know. If you want to prove that, you have to have some insight about waterfalls in Sri Lanka. Like that, to do math certain things, say sequences, then you have to have some knowledge about sequences. So in intuition and insight, you understand the word intuition, no? Some people, so for electric things, they naturally they can do without knowing anything. So that's intuition. These 2 are very important. So by drawing floats, diagrams, graphs of sequences, you get a lot of ideas. They are not proofs. If one plots this sequence, then one says informally, of course, that this sequence does not converge. You can see right away. Because it does not converge to anything. Half the time the sequence is getting close to 1, and half the time the sequence is getting close to -1. That you can see, no? But it is not converging to either of them. For instance, it never gets eventually 1/2 close to 1, never gets eventually 1/2 close to -1, because it is sort of float moving between 1 and -1. It's almost like that. So distance is exactly 1. However, even though -1 and +1 are not quite limits of the sequence, it does seem that in some vague way they want to be limits. They are not limits, but in some vague way. We want, because I have to write on the board. So let me use this also. What are the numbers? 1.1. First number is, let's say this one is 1. Then 1.1 is somewhere here. Next one is minus, let's say this is -1. This is +1, +1, -1. First one is 1.1. Next one is -1.01. Let me draw this line first by dots. This one also by dots. This is bigger than 1. Like this. So here minus 1.01, closer than that guy. Again, this next one is 1.001. Next one is getting more closer to this line. Next one, even closer to this line. Next one, even closer to that line. Can you see? These numbers are getting closer and closer to 1. These guys are getting closer and closer to minus 1. Cannot prove. So in some sense, these ones are converging to 1. These guys are converging to minus 1 in some sense. But the sequence does not converge because distance from here to here is exactly 2. Look at it. So if you take any epsilon less than or equal to, something like 2 or 1/2 or 1, they are not epsilon close or something like that, the word is used. That's why he wants to make this notion precise. We introduce the notion of a limit point. That's why we are going to define, because of this nature, limit point. Let an starting from m be a sequence of real numbers, and let x be a real number, and let epsilon greater than 0 be a real number. We say that x is adherent to an, where it is epsilon adherent. X is epsilon adherent to an if there is an n greater than or equal to m, such that an is epsilon close to s. Epsilon adherent means the sequence is epsilon adherent to x, means there is at least one point. How can I draw? Difficult to draw. Epsilon adherent means, say, here is x. Here is x. Suppose you draw this side x plus epsilon, this side x minus epsilon. X is epsilon adherent. No, A. How does it say? Which way he goes? I should. X is epsilon, yeah. X is epsilon adherent. Epsilon adherent. X is epsilon adherent to an means when you take this interval, at least one an is here. That's what epsilon adherent means. You will take the interval from x minus epsilon to x plus epsilon, some number in this interval, at least one a term lies. That's what it means. Have I put the thing? No. It is here. Then he has another definition. He says if and only there is an n greater than or equal to m, such that an is epsilon close to x. At least one a term lies in between x minus epsilon and x plus epsilon. We say that x is continually epsilon adherent to an. If and only if an is epsilon adherent to an for every capital N greater than or equal to m. Continually means after some capital N, all the terms are in this interval. Continually epsilon, I cannot read these names. Continually epsilon adherent. Continually epsilon adherent means there is a capital N. After that, all the terms are in this interval. X minus epsilon, x plus epsilon. Continually epsilon adding. I have to read this. Then, so you have epsilon adherent, continually epsilon adherent. Now we say that x is a limit point or adherent point of a if it is continually epsilon adherent to a for every epsilon greater than 0. Continually epsilon adherent, we say that x is a limit point or adherent point. Limit point or adherent point means the same thing. No matter which epsilon you choose, x is going to be continually epsilon adherent. If it is a limit point, you choose any epsilon, then there is a capital N. After that, for every epsilon, actually, I mean, change the order continually. X is a limit point. Is a limit point. O, adherent point. Of AN. If and only if. For every epsilon greater than, let me write it.
Try to do.
This one?
No.
This one. If and only for each epsilon greater than 0, there exists n epsilon. This integer depends on epsilon, that's why I put n epsilon. Greater than or equal to n. No, that's what it says. No? This says we say that x is a limit point or adherent point of A. I did I write it correct? Limit point or adherent point of A. If and only if it is continually epsilon adherent to A. So for every epsilon, there is an n epsilon greater than or equal to n such that all of the n's such that for each n greater than or equal to n epsilon an that is limit point now. If x is a limit point, no matter you choose any epsilon, then there is an integer in epsilon. After that, in epsilon, all the terms are in this interval. That's what it means. So, first he said that epsilon adherent, no? Then he said that continually epsilon adherent. Now he is taking limit point or adherent point. Out of them, this is the most important one. Limit point of, both mean the same thing. In topology books, I guess sometimes they use the word adherent point. Some people like adherent point. But analysis people, they like limit point. Because they know the limits. Means no matter which epsilon you choose, after some integer, what it says is but this is how you need to remember. If x is a limit point, no matter which epsilon you choose, after some, depending on epsilon, there is an integer. All of them are very close to x. That's the meaning of limit point. Roughly, forget about epsilon. Limit point means what? But whole many terms surrounded by x. So many terms. Yes.
Is this Sparshonuka?
පුතා ස්පර්ශෝන්මුඛ කියන්නේ වක්‍රයකින් එන එකක් නේ.
It's a continuous function.
This function is discrete, no? Always I know points.
Is it like that?
No. So that is the bad side of this. No examples. Sparshonuka putana, for instance, something like this, y equals 1 over x. This line is, what is the English word for Sparshonuka? Sparshonuka. I forgot.
Cirrus Sparshonuka.
These are Sparshonuka.
Yes, I mean the Cirrus Sparshonuka.
This is cirrus.
Asymptote.
Asymptotes. Very good, thank you. I was going to fail my coordinate geometry test somehow to help. Sometimes some of them are like this, no? You have this. You have this. Bingo. These are asymptotes. No, here is completely different. It is like this. You have the, I will give you examples. You have the terms. You write up here to say you are going to plot the points. You put A1, then put A2. When you put there is a number x, and there is another number y. Suppose you are going to put on the real line, you are going to put a dot or something for the sequence. So A100 is somewhere here. A100 value of this is not from here to here, no length of 1, and this is not this graph. I am just putting the values of A1 on the real line. A100 is here. Then A200 is here. Then A300 is here. A100, A200, then A400 is here. A500 is here. A600 is here. A700 is here. A1 million is here. A2 billion is here. Like that, you get so many points around x. And so many points around y. Very close to y and very close to x. So many. So that is the meaning of x is a limit point. Around x, infinitely many points of A very close. When I say very close as you like, not I like. For around y also, there are so many. Now you may ask me, can you give me such example of a sequence? Shall I give you?
This previous one. Previous one. 1 and the minus 1 thing.
Yeah, this is also 1 actually. This is exactly 1. Minus 1, they are precise. I will give you this. Consider the sequence A given by A, you say 2 plus 1 over n if n is odd. 10 plus 1 over minus 1 over n square if n is even. If you are going to put the dots on the graph, what will happen? Around 2, if you put the lines, this thing on the graph, if you get the number 2 is here, number 10 is here, close to 2, so many points come. If you want, you can write 2 plus minus 1 to the n over then doesn't make sense. You get so many points close to 2. And you get so many, and say if n is odd, if let's say if n is a multiple of 3, multiple of 3, if I will find it difficult to write that. If n is 3k, if n is 3k plus 1, and 15 if n is 3k plus 2, or some k. Suppose this, you get this is your sequence. If n is, this means f is, n is a multiple of 3, no? 3k means. So, when n is equal to 1, you get this one, k is an integer. So, it is 10 minus 1. So, you get 1 point. I mean, you will see that 4, 7, 10, 13. For them, these values are very, very close to 10. Then for multiples of 3, these values are very, very close to 2. For values multiples 3k plus 2 like 5, 11, this sort of numbers, it is exactly fit free. So 2 is a limit point, 10 is a limit point, 5 is a limit point. That's the meaning. It's x is a limit point or adherent point is just for any epsilon, there it is an n epsilon greater than or equal to m, such that for each n greater than or equal to n epsilon, a n let me check early. And I wrote
Comfortable with the definition.
and little bit. The way I have written this, I guess. No, the thing the way I have written is incorrect. That's why. This is why I run. It's good that I wrote it on the board. Because that's the disadvantage of this definition. So it's not clear. I mean, you may read, but cannot get to the head. Can you see it? I'm going to show that, but I have written is incorrect. X is, I'm going to page 140, first line. X is epsilon adherent to an means after n there is one a. One a, like in this graph. This is x minus epsilon. X is epsilon adherent to a means if you take this interval x minus epsilon, x plus epsilon, there is at least one a in this thing. So that is epsilon adherent. Then we say that x is continually epsilon adherent to an if and only if it is epsilon adherent to an for every n greater than or equal to m. That means what I said is wrong. After any capital N, there is some a n belongs to this thing. Not all of them. So, let me erase this and write this again. Without writing like that, just by writing like this, students cannot understand. Now this one is clear. X is epsilon adherent to an means if you take the interval x minus epsilon, x plus epsilon, at least one of the terms an lies in this interval. Now, second one is x is continually epsilon. I am tired of reading this. X is continually epsilon adherent, no? Means what does she say? Says means for every n greater than or equal to n. For every capital N greater than or equal to n. I hope he has written that. Yes. This sequence AM, M beginning from capital N to infinity, is whatever. I will do this language, this epsilon adherent to x is continually epsilon adherent means for every capital N greater than or equal to m. X is
It should be n.
the way I am writing is not good. So what he wants, but is I should write no. X is continually epsilon adherent means for every n greater than or equal to n. X is now it is correct. X is epsilon adherent. So, I wrote this thing in a diary at home. I don't bring the diary to class. Epsilon in going from capital N. Can you see with that? When you say x is epsilon adherent to the sequence, it means you take the interval x minus epsilon, x plus epsilon, one term is here. But if it is continually epsilon adherent, you pick any n, after that n, some term is here. In other words, x is continually, in our English, x is continually epsilon adherent means for every n greater than or equal to m, there is an integer a n, there is an integer a n greater than or equal to capital N, such that a simple n lies here. Right? That's what it means. X is epsilon adherent means you get the interval x minus epsilon, x plus epsilon. There is one term here. X is continually epsilon adherent means you, no matter from where you start, that tail of the sequence is one of, from the tail one term is here. No matter which tail you pick. But x is a limit point means, now you understand, epsilon adherent, continually epsilon adherent, and the last one is limit point. Limit point means we say that x is a limit point. That is true for, it is continually epsilon adherent for every epsilon. Limit point means, limit point, you, no matter which epsilon you choose, actually what it means is, no matter which epsilon you choose, you have x minus epsilon, you have x plus epsilon. For every epsilon, after any n, you get some points in between this interval. So that's why this is going to work Whatever I have written on the board before that is incorrect. That is the meaning of limit I have. Because I got confused with this. Epsilon adherent, continual epsilon adherent, and limit point. Do you understand now? Epsilon adherent means from the sequence at least one term lies in between x minus epsilon, x plus epsilon. Continually epsilon adherent means epsilon is fixed now. No matter from which capital N you begin, after capital N there is one term here. So as a result, there are so many terms. Can you see that? For say you start from simple N. There is one term here. So that is, say that is a 100. Then you choose your N greater than 100. Then again you get another term. Say that is 1,000. Then you say, because for every N, then you get 2,000. After 2,000 again, there is another term coming here. So there are infinitely many terms coming here, but epsilon is fixed. But then limit point means not both of them. For every epsilon, it is continually epsilon adherent. That means you choose epsilon, you take any epsilon, and you choose any n. After that, then there is a term here. Lies in between x minus epsilon and x plus epsilon. Can you see now? So this is not the limit. Limit and limit points are. Can you see the difference? Limit is, if you say limit of, this is a, no? If you say limit of a n is equal to x, what does it mean? For every epsilon, you again say for every epsilon, then you take the x minus epsilon, x plus epsilon interval. All the terms are here. After some capital N. Limit, when you say limit is n equal to x, for every epsilon, there is some capital N. After capital S, N, all the terms are indecision. That is the meaning of limit. Limit point is not that. For every epsilon, actually, there are infinite many terms here, not all of them. You understand? Is it clear? Limit point means, no, you take an epsilon, you take any capital N, after some integer bigger than n bigger than capital N, a n lies here. Can you see? For the limit, after capital N, all the terms are here. So, limit is a limit point, but limit point is not the limit. So, what I had written before is the meaning of limit, because I am tired of this epsilon and the way, this book, no. So now here this one, 2 plus 2 is the limit point, 10 is the limit point, 15 is the limit point for this sequence. This sequence. Right. Is it clear now? Yes. So you have to be precise. You need to write the definitions in your words. You have to say a n, he is beginning from always simple n, no. X is a real number, n beginning from m to capital infinity is a sequence. Then you have to say, in your way you have to write, x is said to be epsilon adherent to a n if there is some simple n greater than capital N, greater than simple n, such that mod of a n minus x less than or equal to epsilon. That is your way of saying it. Then again you are saying x is continually epsilon adherent means for every n capital greater than, for every capital N greater than or equal to M, there is an n greater than capital N such that a mod of a minus x less than or equal to epsilon. X is a limit point of a means for each epsilon, for each capital N greater than or equal to M, there is a simple n greater than or equal to capital N such that mod of a minus x less than or equal to epsilon. 3 statements. X is limit of a means for every epsilon greater than 0, there is an integer capital N such that for each simple n greater than or equal to capital N, mod of a n minus x less than or equal to epsilon. 4 different meanings. So you have to write once or twice and try to get it. The verb adhere. To adhere means much the same as to stick to. Hence the term adhesive. I don't know. Come on, doesn't matter. Unwrapping all definitions, we see that x is the limit point of an if, now he is saying if for every epsilon greater than 0 and for every n greater than or equal to m, there is an n greater than or equal to n such that, so he has written what I said. Why is this the same definition? He is asking why, and it goes without saying, you can say, note the difference between a sequence being epsilon close to L, which means that all the elements of the sequence is stay within the distance of epsilon, and L is being epsilon adherent to the sequence, which only needs a single element of the sequence to stay with the distance epsilon of L. I guess these two lines are clear. Also, for capital L to be continually epsilon adherent to an, it has to be epsilon adherent to an for every capital N greater than or equal to M. Whereas for an to be eventually epsilon close to L, we need an to be epsilon close to L for some capital N greater than or equal to M. Thus, there are some subtle differences. He is using the word subtle, very good, in quantifiers between limits and limit points. So you have to be very clear about limit and limit points. So you have to go through this. Epsilon adherent means, continually epsilon adherent means, and limit points definition. You must be very clear. Very, very clear. You must be. Note that limit points are only defined for finite real numbers. It is possible to rigorously define the concept of plus infinity or 1 means being limit points. See exercise 6.4.8. So if you want, you can define it. So that's what I guess he is doing in 6.4.8. So that will not be a big deal anyway. Example. Consider the sequence. The number 0.8 is 0.1 adherent to this sequence. Since 0 point is 0.1 close to 0.9, which is a smaller member of this sequence. However, it is not continually 0.1 adherent to this sequence. Once one discards the first element of this sequence, there is no member of the sequence to be 0.1 close. Clear? Because continually adherence means for every capital N greater than or equal to N, there must be an integer greater than capital N close to with the distance of epsilon. So it's not happening here. On the other hand, the number 1 is 0.1 close to adherent to the sequence, and in fact it is continually 0.1 adherent to the sequence. Since no matter how many initial members of the sequence one discards, there is still something for 1 to be 0.1 close to. In fact, it is continually epsilon adherent for every epsilon, and is hence the limit point of the sequence. Actually, for the sequence, 1 is not a limit point, actually 1 is limit, no? Limit is 1. Now we just consider the sequence 1.1 minus 1.01, 1.001 minus 1.3071, like that. The number 1 is 0.1 adherent to this. Now you can go through this paragraph, no? Understand? No? So you need to be very clear about the definition. When we just write using English only, it is not that clear. You have to write in your own English. Okay, now limits are of course a special case of limit points. This is limits are limit points. Let A and be a sequence which converges to a real number C. Then C is the limit point of A again, and in fact it is the only limit point of A. No, it is clear now from the definition. To be a limit point for every epsilon, and for every n, there must be an integer greater than that capital N, which lies in the interval x minus epsilon, x plus epsilon. That is limit point. So when you see that, I mean, very easy to prove limit is a limit point is trivial. You can prove it, no problem. But however, very important to write precisely. Sometimes things are, you know it is true, but you cannot write in correct sentences. You have to learn to write. So that's why I decided to grade 1 or 2 questions that you write the solutions. Okay, now we will look at 2 special types of limit points. The limit superior and limit inferior. Let's see. So 2 words, limit superior and limit inferior. Suppose that you have a sequence, right? I use the word tail of a sequence. Is tail in this book? No. Anyway, tail you can understand.
It says eventually.
Tail of a sequence is, you begin, the sequence is starting from somewhere. Before, say for instance x1, x2, x3. Say this sequence. So you say this is x1 plus k. This sequence is a tail. This is x2, x3, x4, like that. Or else x3 plus k. This begins from x4, x5, x6, they are tails.
In the book, it says eventually.
No, he has eventually means something else. Eventually, when he says, given any capital N, something bigger. This is always different. That's why I asked you, like always. Spell like 2 months, 2 more months, you will catch it. You have to be better than in writing, no? Because sometimes you may find it difficult to be as good as me in thinking because I am mature. I have seen quite a lot of things. But you must be better than me in writing because now I cannot say now I don't work at home. Book is new, I am working harder than you do. Okay, so let's come to this lim sup lim problem. You have, now I am writing the sequence. What is the sequence? AM plus 1, AM plus 2, AM plus 3, AM plus 4, AM plus 5, AM plus 6, AM plus 7, like that. goes forever. Now he is saying simple an plus. A capital A plus upstairs is equal to supremum of this sequence an going starting from capital N to infinity. An plus. That means he goes somewhere here. He starts from an, then he goes to an plus 1, an plus 2. He looks at the terms starting actually this tail, because I told you the meaning of tail. He looks at all these terms. Supremum of this thing is written as an plus. Right? That is the, so he has a m plus 1 plus, no? He has a m plus 1 plus. Like that he gets. So this is a new sequence. You have the sequence an. He goes to a term. He looks at all the terms starting from that term. Get the soup. That he says, if he begins from n, he says it is an plus. So he starts from here, an. He takes the supremum of all the terms in the sequence. He calls it an plus. Then he forgot about the first term, goes to the second term, look at all the terms in this sequence from this term, call it an plus 1 plus, like that. So from this sequence he got another sequence. Similarly, okay, before that he says more informally an plus is the supremum of all the elements in the sequence from an onwards. Now he comes to formal English. We then define the limit superior of the sequence an come to denoted by lim sup. Limit superior is this. Limit superior lim according to this book. Lim sup. How does he write? Here and next. An. Lim sup of this sequence, he says, now he has this an plus sequence, infimum of, is that how he writes? I have write the way he writes. N plus, oh, I write plus in the wrong place. N equals N to infinity. So in other words, now you understand now an plus 1, an plus. What he does is, he has the sequence. He finds the supremum of all of them. He wrote it here. He go to the next term, forget about the first term. Then he look at all the terms starting from here. He writes the supremum here. He forget about the first two terms, go to the next one. Then get the supremum of all the terms. Now he get a sequence. Now this sequence he get the infimum of this sequence. Infimum of this sequence is called lim sup A. That is the lim sup. Right? Got it?
I'm wondering why he used the lim sup and this is imp.
Yeah. You asked me a very good question. This is not how I define lim sup. I define lim sup in a way which answers your question. That's how I define. Because now it is kind of, somebody can wonder, no, why on earth we do this thing? Don't we have anything else to do? Like you ask me why lim soup. There are reasons. Anyway, this is correct. But one comes to the question you ask. Again, lim inf. Now you can guess how he defines. You start from here. You find not the soup but inf. He says it is an minus is infimum of an n going capital N to infinity. An minus is, for instance, he goes to first term, he look at all the terms, he get the inf, he call it An minus. Then he discard the first term, delete the first term, go to the next term, look at all the terms, find the inf, he call it Am plus 1 minus. Then he delete the first two terms, get the rest of the terms, find the infimum, he writes it as Am plus 2 minus. Is he writing capital M? No. Like that he does the job. Now you can understand, he writes lim inf n tends to infinity An to be here over there. Here he wrote inf. Now he must be writing soup. Soup of An minus n going from n to infinity. These are the two definitions. You may not be anywhere, no? You may not be anywhere. I can see that. Now, anyway, something good is that he has some one or two examples. Let's look at them. And actually on page 143 and 144, leave all the results in one proposition. I wonder whether you can do it, but I will try to get you somewhere. Before that, let's go through the examples. 6.4.7. I'm not going to, if you want me to write on the board, you tell me, otherwise I will just read. Let example 6.4.7. Now anyway, whether you didn't get any feeling or not, you understand the definition, no? You wonder why on earth we define like this, but to the contrary, you got it. No, you will get that. But if I have defined the way I like the definition, you definitely understand. So, this is not, I suppose, read differently, but you know, he may be having other, he's a real big person, other motivations. Okay, let's look at this example. First term is 1.1. Next term is minus 1.1. Third term is 1.001. Next point is minus 1.30 Next point is plus 1.40 Now let us try to write A1 plus. A1 plus is what? Supremum of all the sequence in the sequence. So what is the biggest term? 1.1. So A1 plus is 1.1. Now we delete first term. Then we want to find what is the supremum of the remaining terms. What is it?
1.00.
1.00.
0,
0, 1. So A2 plus is 1.001. Now we delete second term also. Now we begin from 1.001 etc. So what is the supremum of these terms? 1.001. Can you see 1.0 A2 plus is 1.001? A3 plus is also 1.001. Now you delete first three terms. So what is the supremum? 1.4071. Now you delete first five terms, 1, 2, 3, 4. How many terms? 1, 2, 3. 4 terms you get 1. If you delete 5 terms, you don't have that many terms written on the book. Anyway, now you understand, no?
Yeah.
To compute, if you are given like this, you know how to compute A1 plus A2 plus and so on. Only thing is you have to be patient, no? Because sometimes somebody can want A2 plus is 1.001, A3 plus is also 1.001. Why? Must be wrong. But you have to be patient and see how to do it. He is asking why. I mean, why we don't have to answer. And its infimum is 1. Because you are getting 1.1, 1.20 and 1, then 1.40 and 1 twice, no? Again you are getting 1.60 and 1, 1.80 and 1. That's how you are going to get. So infimum of this is exactly 1. Therefore, lim sup of this sequence is 1. Right? Hence the limit superior of this sequence is 1. Right? 3 for this sequence. Now let's find A1 minus. What is A1 minus? Starting from the first point, what is the infimum of the sequence? Whole sequence. First, second,
minus
third,
1.0.
minus 1.01. So you delete the first term of the sequence. Then what is the infimum of the remaining terms? Again minus 1.01. Then you delete the first two terms of the sequence. What is the infimum?
Minus 1.301.
Minus 1.30 and 1. You understand now, no? Again next term also will be minus 1.30 and 1. Like that you get minus 1.01, minus 1.01, then minus 30 and 1 twice, then minus 1.50 and 1 twice, minus 1.70 and 1, like that. So what is the supremum of this thing? Supremum is minus 1. So hence the lim infim will be minus 1. One should compare this with the supremum and infimum of the sequence, which are 1.1 and minus 1.1. Infimum of the supremum of the sequence is 1.1. Infimum of the sequence is minus 1.01. But now we got lim sup is 1, lim inf is minus 1. They have nothing to do with supremum and infimum of the sequence. They are very different. Right? Now let's go to the next example. Let A1, A2, A3 denote the sequence 1, minus 2, 3, minus 4, 5, minus 6, 7, minus 8. So what is A1 plus? Starting from 1, so this is the sequence starting from 1. What is the supremum of the sequence?
It doesn't have one, so or plus infimum.
It is not bounded above, so plus infinity. Then what is, you get rid of the first term 1, then starting from minus 2, 3, minus 4, 5, minus 6, 7, what is the supremum? Again infinity. So can you see continuously A1 plus A2 plus A3 plus all of them are going to be infinity. Therefore lim sup also will be infinity. Similarly A1 minus, what is the infimum of the whole sequence? It is not bounded below. So it is minus infinity. If you get rid of the first term, still remaining terms have infimum minus infinity. So A1 minus A2 minus A3 minus all of them are minus infinity. Therefore lim inf is also minus infinity. So we got that far. Now let's go to example 6.4.9. Let A1, A2, A3. Let A1, A2, A3 denote the sequence, 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth minus 1 over 6, like that. Then you have even number in the denominator, you get the minus sign, odd number plus sign. That's the sequence. Okay, so what is A1 plus for this sequence? 1. The biggest number is 1. If you delete the first term, 1 over 3. If you delete the first two terms, what is the supremum? 1 over 3. If you delete the first 4 terms, what is the maximum? Supremum 1 over 5. You get the pattern, no? So then A1 plus this sequence, which has the infimum of this sequence is 0, because this is like 1, almost like 1 over n, but not 1 over n, because 1 over n appears twice, 1 over n, 1 over n. Similarly, if you look at A1 minus, if you look at the A1 minus, what is the infimum of the sequence? Whole sequence? Minus 1 half. If you delete the first term, it's still minus 1 half. If you delete the third term, 1/3, what is the infimum? Minus 1/4. Even if you delete the first 4 terms, including minus 1/4, like that, you get the pattern, no? This you understand now, which has the supremum of this one is also 0. So where am I? I can see. So the limit superior is 0 and limit inferior is also 0. Both are equal to 0. Now let A1, A2, A3 denote the sequence 1, 2, 3, 4, 5, 6, like that. If you take A1 plus, this is not bounded above, so it is A1 plus, A2 plus, A3 plus, everything is plus infinity. So limit superior is infinity. Similarly, A1 minus, A2 minus, again plus infinity, all of them. So the limit inferior is also plus infinity, no? Plus infinity. Alright, so he says some authors, he wrote lim sup, he wrote n arrow, infinity below sup and below inf. Insert, some people write this way, many people, then I say some, this way. This is lim sup. And this way. This is lim. This is way of writing. Some people write like that. Many do actually. They maybe soup above, inch below, maybe that kind of thing. So far, understand, no? Those people, they put this arrow also here. I don't put. You know, different people, different ways. It doesn't matter, but you need to know because after 6-7 months you may read another books. You will be able to read some other books. If you are reading another book, read the easiest book in the world. Because you are learning. That's how. Otherwise, if you read a very difficult book, you get discouraged. I don't understand anything. What this you will say. All right. So let's read this paragraph. Return to the piston analogy. Piston analogy you can read and understand. No? Oh, you want me to read?
Is it going to explain this?
I finished this, no? After that, you come to this piston analogy. If you want, I can go through, but you can understand.
Yeah.
It's not. We now described some basic properties of limit superior and limit inferior. I guess he has written roughly everything about limit superior and limit inferior right away. So I would like to explain certain things before I go start. Before proving, actually I want to explain the theory. Now, for instance, Pythagoras theorem or Pythagorean theorem, maybe you cannot prove. Now, if I ask you to prove it, I'm sure you cannot. I cannot, maybe. I don't know, maybe I can. You know, I'm kind of very serious. But maybe you cannot prove it, but you can use it. Very well. Like that, even if you don't understand this theorem, statements, if you can use it, you are in good shape. I want to prove it. Say suppose A and B are subset of R. A is subset of B is subset of R. Assume B is bounded above also. Assume A is bounded below. I write B, D, D because I am lazy. And B is bounded above. Therefore, both of them are bounded above and bounded below. No? If B is bounded above, certainly A is bounded above. Now I will draw a picture. This is my A. This is my B. Now from the picture you can say something about soup A and soup B. From the picture, what can you say about from the picture? About soup A and soup B? Something.
Soup
Less
is less
than
than.
or equal to.
Very good. And you can say something about inf A and inf B also.
If A is greater than or equal to.
So these are two facts very important. This is from the picture, we should prove them, and if A is subset of B, sub A is less than or equal to sub B. However, if goes other way around, inf A greater than or equal to AB. Proof. Let's prove. Assume these sets are unempty, so otherwise it doesn't make any sense. So I am going to prove sub A less than or equal to sub B. Right? Now, sub B is a finite number. I said I am not writing all of them. B is bounded above, therefore sub B is a real number, finite number. Right? So now let A belongs to A, because A is, without writing that, I can write this way also. For each A belongs to A. A belongs to B. Let me write without being pandit. Another case better for you. Let A belongs to A. Then A belongs to B. So, A less than or equal to sub B. Every element of A less than or equal to sub B. Every element of B less than or equal to sub B. However, A, now therefore, for every A belongs to A. A less than or equal to sub B. Therefore, what can I say? For every element of A less than or equal to sub B.
Therefore, sub A is less than or equal to sub.
Very good. This says sub B is an upper bound of A. No?
Yeah.
Therefore, sub A less than or equal to sub B. Prove first one. Yeah, I have proved the first one. Now let's go to Roman 2. Right? Again, let's begin say whether let A belongs to A. Then A belongs to B. Any element of B greater than or equal to inf B. Therefore, so A greater than or equal to inf B. Thus, for each A belongs to A, A greater than or equal to inf B. So this one says inf B is the lower bound of A. And something else now you can say. What can you say?
Inf A is greater than or equal to inf B.
This one says inf B is the lower bound of B, but inf A is the greatest lower bound. Therefore, inf A greater than or equal to. Right? That much we proved. We have proved that. Now I am going to use it. You want to copy or shall I erase it?
Give me just take a photo.
Right? So, I'm going to clean the board. Now let's come back to this thing. You are given, let A be sequence of real numbers. Okay. So all these are real numbers. Now, you consider this set. AM plus 1, not A. What, let's say, not A, not M, I. AI plus 1, AI plus 2, then, no, let me write one more. You agree for this, no? For any AI plus 1, AI plus 2, AI plus 3 is a subset of that guy. Therefore, supremum of this guy less than or equal to supremum of that guy. And we proved, no? A is subset of B, should be less than or equal to should be.
So shouldn't it be the other way?
Shouldn't it change?
I am tired, I guess. I want to write it here. Let me put it this way. You are not sleeping, no? Good. Yeah, plus 3. This guy is subset of that guy. Therefore, supremum of AI plus 1, AI plus 2, AI plus 3. No. It's less than or equal to supremum of and infimum of this guy greater than. It's good that you are not sleeping. Dangerous teacher. Infimum of thus, that is 18 name. According to our symbols, this is simple AI plus 1 plus greater than or equal to simple AI plus. Am I right?
Less than or equal.
Less than. And AI plus 1 plus less than right. Here AI plus 1 minus greater than or equal to AI minus. Right? Now it is correct, no? Hence, this is a Therefore, A, what are the symbols? This guy is using so many organic things. A, N. N plus n going n to infinity is a what kind of sequence?
What am I going to can't do
AI plus 1 because according to the AI plus 1 less than or equal to AI plus. What is happening here?
Increasing.
Decreasing. So this is a decreasing sequence. And an plus minus n going m to infinity is n increasing. Right? A plus this one is decreasing. This one is this one is increasing. Before a while we studied every increasing sequence converges to a real number if it is increasing, not converges if it is bounded above, otherwise leave it as infinity. Decreasing sequence again converges to a real number if it is bounded below, and otherwise it goes to minus infinity. Therefore, and what is important thing is that now this lim sub a n etc. If by any chance before we prove this theorem, I am not going to actually, this is an exercise. We wonder whether one can he writes so many things in assuming that you two are the brightest in the world. Can you see, even though he has written the proof freely, let's assume it is bounded. Then we can think of it is bound on whether it is bounded above, bounded below, this and that. Before we prove this theorem, we have to prove. Not that before you prove this theorem, I have to tell you many things. Now, anyway, now we know that an plus 1 is a decreasing sequence, an minus is a decreasing sequence. If you start from a sequence bounded above, can you see that an is also bounded above? An plus is bounded above and bounded below. If the original sequence is bounded, an plus is also bounded. Can you prove it? Suppose the whole sequence, are you with me?
Yes.
This one. Suppose the whole sequence A for each n belongs to N, an is. So we are not really doing his theorem, but we are going to restrict to a bounded sequence to make us feel at home. Otherwise, you will not be anywhere. Suppose an is bounded, so any n term is in between minus m and capital M. Therefore, if you take, now I want to show that, I want to know whether this sequence, A plus sequence, it is bounded above and bounded below, that sort of thing. Then you prove that A plus 1 is bounded below, because then you can, it converges to lim inf. If this one is bounded above, it converges to sup of the sequence. Can you prove that this one is bounded below? If you take any, if you now take for this set, say let's take this set, any term is in between minus m and plus m. Therefore, its supremum is also in between minus m and plus m. So, all the terms are less than or equal to minus m or, sorry, less than or equal to plus m or greater than or equal to minus m. That means this sequence is bounded. This one is also. Therefore, if you start from a bounded sequence, this is a decreasing bounded below sequence, this is an increasing bounded above sequence. Therefore, they are expected limits in the sense a n plus 1 converges to sub infimum of a n plus and a n minus converges to supremum of a n minus. Right? So now when whether he writes, he wrote infno, lim sub infinite is equal to inf. Actually, this is the limit. No? Lim a n plus, even though we wrote inf, because it is decreasing, it converges to inf. As a result, if we want, we can write lim here. Over there also we can write limit. So we got this form. What we know is a n plus 1 is a decreasing sequence, a n minus is a decreasing sequence. Both of them are bounded if the original sequence is bounded. Therefore, we have these limits. And now I am trying to give you some idea about this. No, that's what I am doing here. Now let's go to the statements of the theorem. Before you prove, now I am going to, you got this much now. Got this much. So now let's go to page 6 point. Oh, where? Yeah. I erase, no? No, in his case, he used the word El Pasco lim sub in his theorem. No? L plus. Let A be a sequence of real numbers, let L plus be the limit superior. Lim sub, you know the meaning of lim sub. That means you take supremum of the tails and the limit of it. Actually, it is a decreasing sequence. So lim sub is that, and you know the lim inf. Lim sub, he used sub, he had capital L plus, capital L minus for the lim inf. Thus both L plus and L minus are extended real numbers. We are in the case, they are real numbers to make us feel about it. So, if you go to the what was to be proved, part C, because I am trying to give you the feeling of this thing. Part C, he says, infimum of a n going m to infinity, less than or equal to L minus, less than or equal to L plus, less than or equal to the supremum of a n going m to infinity. So, what is most important here is, he is saying L minus less than or equal to L plus. We have to prove it. We have to prove it. L minus. So, if you think of a picture, so L plus may be somewhere here, L plus, L minus is somewhere. After proving the theorem, L minus must be below L plus. Okay. And infimum of a n going m to part C says it is less than or equal to L minus. Maybe there are terms below L minus, that means, and the supremum is greater than L plus, there may be terms above L plus. So, now let us look at the part A. Part A. For every x greater than L plus, there is an integer n greater than or equal to m, such that a less than x for all n greater than or equal to n. Now you have got, you know the meaning of L plus, you know the meaning of L minus. Now it is clear now, no? How we came to L plus. We got the limit of, you got the supremum of the tails, no? Tails and supremum of the tails. Then you got the limit of that, actually infimum of these supremums is called lim sum. That is L plus. Then you got the supremum of the tails. They are increasing, and its limit is infimum of these supremums. So we have to prove L plus less than or equal to L minus. And if you take any number x, let's draw it in, by the way, darker line, otherwise difficult. I have to draw it again next day. If you take any x greater than L plus, any x greater than x plus, now I am drawing a dotted line. These dots must be erased. Like that. This is L plus, and this is x. You take any x greater than L plus. So x is like L plus epsilon. No? Actually, for any epsilon greater than 0, in analysis language, what does it say? It says there is an capital N greater than or equal to m, such that a less than x for all n greater than or equal to m. If you draw that, if you are thinking of the graph of an, this side is an, this side is n, what it says is there is some capital N somewhere here after capital N. All graph will be below here. I mean, it's not a continuous graph because
Yeah.
point graph, but below that line, no matter how small epsilon you choose, then L plus epsilon is your x. There is some capital N. Before that, it may go to Buffalo, New York, downtown Florida, Pittsburgh, etc. But after that, all of them are below x, L plus, x or in our language, L plus epsilon. For each epsilon greater than 0, there exists n epsilon such that for each n greater than n epsilon, a n less than L plus epsilon. That is the first part it says. Now what? The elements of the sequence n eventually less than x. Let's not read the line about L minus. Then I am going to part B. So still I am looking at part A only. Part A for in his language, for any number x less than L plus, greater than L plus, there is an integer sum according to him nx such that after nx all the terms are strictly less than x. According to analysis language, for any epsilon greater than 0, there is an integer n epsilon such that for every n greater than n epsilon, any a n is less than L plus epsilon. Both of them are telling the same thing, no? Okay, now I did not read the line about B, line about L minus. Now I came to part B. For every x less than L plus. Now every x less than L plus. In our language, for every epsilon greater than 0, I am considering L minus epsilon. Any number less than L plus is of the form L minus epsilon for some epsilon greater than 0, because I try to bring epsilon when you are doing analysis with epsilon ball game analysis is. Anyway, for every x less than L plus and every capital N greater than or equal to n. Let's draw now here. Now you go below. Now you exist below here. That you no time. Because I must go home before. Let's talk about other day. That is what to say. The reason I am going through this, I kind of was surprised that he did everything so fast that even what I told you so far, without my explanations, you could have find it difficult to learn. No? Anyway, so let's get today. Next day, we should learn lim sup lim inf very well, and limits sup inf. So when you are if you want to be an analyst, you should be like that. According to here, what is another bad thing is about. Now, about here, he is using. In a way, this sequence has both finite lim sup and finite lim inf. I would like to have a graph which has a finite lim sup, but infinite lim inf, negative. Another graph, I would like to have a graph which has a finite lim inf, but lim sup is infinite. And finally, I like to have a graph, lim sup, lim inf, both are finite. So to understand very well, we have to go through these three things separately. Okay, so another day.